All right, so on this question, I will just cross this part off. What that means is by actually taking the integral, but you don't know how to, the whole point of me putting this question on there is you don't even know how to do that integral. So, but you can use the second fundamental theorem because you don't actually have to know how to take the integral to do that, right? So what would the answer be here?
E to the negative 2 times x times y.
Good. Right, so you're just, it's gonna be e to the g of x, right? So we're just gonna plug that in wherever we have our independent variable. Times
4x to the
4x cubed, times the derivative, times g prime of x. So times 4x cubed, and we'd probably just put all that stuff out front, right? But that's it, okay? Good. Okay, what I want to do, I just want to show you something, get you started thinking about something. This is going to be really minor, not a big deal. Okay, what about, let's take a problem like this. What if we have something like the integral of something like that, okay? Just an indefinite integral or antiderivative. How would we do that? At this point, we will, by distributing, we'd expand it out, right? We'd have to multiply out the x squared plus 1 and then distribute the 2x, and then we'd get a polynomial, so we could just term by term take the antiderivative, right? And that would work. That's fine. Okay, how about one like this? And this doesn't seem like this is that big a deal. I won't even let you suffer with this one too long because the answer is you can't do it. It doesn't fit one of our very limited standard forms, does it? Right? We could do, you guys could do this. You could do the antiderivative of sine x dx. Right? What's that? What is it? Negative cosine x plus c. There you go. Okay. But that's not what that is. That's a different function. It's 5x. Right? So let's go back to this first example for a second. Even with this one, you can avoid having to do all that pre-writing of the problem, having to expand it out and distribute. Okay, there's a trick here. Everybody see the trick? Our goal is we would just like to make this into a simpler looking integral. And the trick is going to be a substitution. This is the most common technique for solving integrals beyond just, I mean, really think about how limited we are. You've got a sheet of integrals or antiderivatives, and you have, how many have we talked about at this point? Maybe 12 at the most, right? That's it. That's all you can do. That's not very much. There's all these other ones that are sort of like those, but they don't match them perfectly, right? So the most common way to expand your ability to do antiderivatives is to make what's called a U substitution, which is what we're going to do here. Now let's just look at what would happen if I were to pick something like, for example, what if I were to let U equal x squared plus 1? Okay. And that's a good choice because that's the argument of this power function, right? That's what's being squared. If U is x squared plus 1, sounds like I'm using bad grammar there, what's du? And this is just, we haven't talked about this in a little bit, that's just a differential form of the derivative. 2x, no, not plus c, but that's, we're just taking a derivative this time, right? 2x dx, right? Okay, you see why? Because here's kind of the missing step there. If u equals x squared plus 1, then du dx equals 2x So u equals 2x dx, right? Okay? Well, now look what happens if I make a substitution here. Look how easy this problem becomes. What does this integral look like if I make that substitution? Not x squared, it'd be u squared, right? So I'd get u squared times du, right? Look at that. That's like magic, right? Now, what's the answer to that one? That's easy. Say it again, u cubed over 3 plus c. Now, what's the only thing I've got left to do here to get my answer in terms of x?
Just plug it back.
Yeah, reverse the substitution, right? So then we just end up with the quantity x squared plus 1 cubed over 3 plus c. Amazing, right? Okay. So that's what we call a u substitution. What did we just do? Well, this is kind of what it looks like in terms of, in a calculus book, right? If you've got a composition of functions, is what this is, f of g of x. In our case, f of x is what? If it's a composition, if it's f of g of x, f of x would be x squared, wouldn't it? Right? The outside function is squared, and then what's inside the squared function, the power function? Well, x squared plus 1, right? So it's f of g of x. So if you've got the integral of f of g of x times the derivative of what's inside, g prime of x dx, then that's equal to, ultimately that's going to equal the antiderivative of f of g of x. But it's much easier to think of, much easier to look at and think of if you instead think of that interior function g of x as being u. Now you have to be careful when you say this, but then we've got the antiderivative of f of u du equals capital F, right? That's the antiderivative, f of u plus c. Then you just reverse the substitution and plug in g of x. Okay? So let's try, and that's, honestly, I mean, we'll look at this one time. And now, but you're always just going to think of it as being, you're just going to pick a u and go from there, right? I mean, you won't ever really, this is the technical mathematical mumbo jumbo that explains what we just did, right? The process of substitution with kind of the mathematical fine print. But you'll see here in a second that it's much easier to actually use this. What are we going to pick for our u here? 5x, good, because that's what's inside the sine function, right? That's what's complicating things, is the fact that this isn't just a sine x, it's a sine of 5x, right? So if we let u equal 5x, what's du? 5 dx, everybody agree? Okay. So what have we got here then? Let's circle the stuff that we have. Well, I've got a sine of u, right? And then here I've got a dx. So if I were to solve for dx in terms of u, what is dx equal to? Du over 5, good, right? So when I make my substitution then, what I really get is the integral of sine u times 1/5 du, right? Now, where should I put the 1/5 though, do you think?
Out front.
Yeah, might as well just put it out front while I'm writing. There's my 1/5 du, and so what's my answer? Okay, so we get negative 1/5 I've got out front, cosine u plus c. Let's reverse the substitution, and what's that become? Done. Got that. Okay. Let's try another one. Just get a little practice with these. Okay, how about, real quick, just, we'll take a quick look at this list. This is just out of your actual textbook. Guidelines for making a change of variables, essentially for choosing the right U. You know, it's not like there's some stuff that always works, but you guys already probably have a sense of this. I mean, Paige chose the U she did because it just was intuitive that you want to pick what's inside the function, right? So when you're choosing a U substitution, usually it's best to choose the inner part of a composition of functions, right? Such as a quantity raised to a power. And then we're just going to calculate du like we did, right? Du is just going to be the derivative of what's inside times dx, or times, times whatever we chose for u. We rewrite the integral in terms of u. We solve the integral in terms of u. And then we reverse the substitution, okay? All right, so let's try another one. How about something like, take a second and just try that. Now, admittedly, we could do this without a u substitution, but it would be pretty ugly. Ideas. Suggestions for a u substitution here. X squared minus 1. Okay, so if we let u equal x squared minus 1, what's du? Okay, so let's make our substitution then. So we get the integral of what? U to the fifth. And then now, yeah, good. What we've got an x dx left over, right? So what's that going to work out to be? There's an x dx.
1/2 du.
Okay, 1/2 du. So what's the solution? Okay, good. Yeah, so we get u to the 6th over 12 plus c. And if we reverse the substitution, then we'll just plug in our u, right? So we get the quantity x squared minus 1 to the 6th over 12 plus c. Okay, what about, let's do a trigger. Okay, this one's a little trickier. Suggestions for a u here. Cosine, good. Now why not sine? Say it again. I mean, you're. I know you know what you're doing on this. I can tell.
We know how to differentiate sine or whatever, but not a cosine cubed.
Okay, not a cosine cube, right, right. And even if I had an easier one, like let's just say we were deriving the, okay, let's say what if we were gonna do this one? What if we were gonna do the integral of sine x over cosine x? Which one would we have to pick for our u? Which one? The cosine, right, because, and we still can't, we actually can't do this one yet. We're missing, even when we write it, well, let's just set it up, and then we'll get to a point where we won't know how to proceed. For now, we will soon. But if I picked, look what would happen if I picked u to equal sine x. What's du? Cosine x dx. Well, what's the problem there? Yeah, all I've got here is, I've got u, but the cosine's in the bottom, right? See what I'm saying? So when you do this stuff, and I think a lot of you have already figured this out, you almost want to work backwards a little bit. You almost want to look at this and say, okay, well, I've got a sine x dx on the top. That's probably going to, that's like a du, isn't it? So the derivative of what's going to give me that? Well, it works out because I've got a cosine on the bottom. But you can't end up with a du that's got a cosine on the bottom, right? So you have to almost think one step ahead. You can't just always pick a u based on what seems like the right thing. In the back of your mind, you got to think, well, I also have to be able to get a du out of that, right? So if we go back to this one then, in this case, maybe it's a little clearer. So u equals cosine x. What's du?
3 cosine.
Negative sine x. Negative sine x.
Negative sine x.
We don't want to do cosine dx.
Right, now we got to pick the bottom function. In this case also because that's the one that's inside the power, right? Think what cosine cubed means. Cosine cubed x just means the quantity cosine x cubed, right? That's our shorthand for it. So then the cosine is what's inside that power function. So that for that reason also is a logical choice for our u. What am I missing here? Dx. Okay. So now let's make our substitution then. So we get cosine of x quantity cubed is what in this case? No, and the du can never, it always just has to be linear, right? We just have to have a du. But if cosine is u, then what's 1 over cosine cubed? Say it again?
1 over u.
1 over u cubed, and if we want to do calculus on that, how would we write that? U to the negative 3. Everybody see that? Right, this is the same thing as saying 1 over cosine x cubed, right? We've just got like that, don't we, inside our integrand? And so we'd want a u to the negative 3. That's what that part did. And now what about this other part here? We've got a sine x
So we're going to have to
dx. What is that in terms of du?
negative.
Negative du. So where's the negative go? In front, yeah, it's constant. Okay, so what's that give us? Okay, and the negative will actually cancel, won't it? Right? But I'm going to get, say it again, I get u to the negative 2 over negative 2, right? Good. So that gives us u to the negative 2 over 2, because that negative cancels, plus c, right? And reverse the substitution and we're done. So what's that look like then? Yeah, good. So I get 1 over cosine 2 cosine squared x, right? Plus c.
How do you get from the negative wiggly noodle u to the negative third u to the u to the negative second over 2?
To this, well, because what's the antiderivative of u to the n? Right, u to the n plus 1 over n plus 1. Negative 3 plus 1 is negative 2. Okay? What about this one then? If we complete this substitution, we would just get the integral of, let's see. Yeah, this one's the one that didn't work, right? That was our bad choice. We'd want to pick u equals cosine x, so du is negative sine x dx, right? What did we get this time? Negative, say again, du, du. Okay, how could we solve that? It's like u to the negative 1, but the formula falls apart there, doesn't it? Right, think about that. The antiderivative of u to the negative 1 du by our formula should be u to the 0 over 0. Well, that's a problem, right? That's clearly not the right answer. So our power formula doesn't work for that one. We don't know that one yet. Okay, that's what we'll have to add a little bit later. That's probably the last section we'll do in the class, is talking about this kind of stuff, okay? But at least we were able to make a substitution. Okay, let's try one more. I think that's probably a good intro for today. How about, oh, I know one thing I do want to do. Yeah. Okay. Yeah. Okay, could I do this one without making a substitution?
Yeah.
How?
Oh.
See the problem here?
Yeah.
The problem is I've got this 2x minus 1 inside the radical, right? And there's no way for us to deal with that. We don't have a standard form that looks anything like that, right? So what's probably my u substitution got to be here? 2x minus 1, right? And it has to be because that's the part that we can't deal with. We can't have the square root of a polynomial, right? We can deal with the square root of just a number, a variable, that would be fine, right? That's just something to the 1/2 power, right? We can use the power rule for that, but that we can't deal with. So we'll make this substitution, u equals 2x minus 1. Okay, so now what does that make du?
2dx.
Okay, so if we make our substitution, what do you notice here then? We've got the integral of u to the 1/2, right? So that one's taken care of. That becomes u to the 1/2. And dx, if we solve for dx, what's that?
1/2 du.
Okay, good. So then that part becomes 1/2 du. But what do you notice?
So an x.
Yeah, we still got an x. That's what we call an incomplete substitution. Right? Now, we obviously can't have mixed variables there. Right? We can't do calculus with two different kinds of variables. So, at least this year we can. What do you think we could do?
Use our substitution and solve for x.
Yeah, we could go right back up to our substitution rule and solve for x, right? So if u is defined as 2x minus 1, then what's x equal to?
U plus
Okay, so we could make that substitution, right? And we end up with 1/2 times the integral of, I'm gonna put the u to the 1/2 out front, not that it really matters, times, let's pull the 1/2 out front, how about? What, so we get what out front then? 1/4, okay? Oh, darn. Okay, so now I've got the square root of u times the quantity u plus 1 du. You might think, well, that helped a lot. We had something times a square root up here, but it did help a lot. We can deal with that, right? What do we do there if I want to solve this one? What can I do? Well, I can't plug u in until after I've done the integral, right? The whole point of the u substitution is so we can do the antiderivative more
Are
easily.
we gonna have to expand it?
Yeah, well, we could just distribute, couldn't we, right? If I distribute the u to the 1/2 here, what do I get? Plus 1/2, good. And that we can solve. So what's that equal to? What's the antiderivative of u to the 3/2? Say it again.
2/5.
2/5 u to the 5/2. U to the 5/2 over 5/2, right? But dividing by 5/2 is just multiplying by 2/5, right? Plus, how about this one? U to the 1/2 must be u to the, what's 1/2 plus 1?
3/2.
3/2. U to the 3/2 over 3/2, which is times 2/3. See, so we actually, this time it was okay. Having a square root wasn't a big deal because it was the square root of a variable, so we could just distribute that over our polynomial, right? And now all we do is reverse the substitution, and we're done. What was our u again?
2x minus 1.
2x minus 1. So there it is. Okay. All right, how much time we got? Let me see. Oh, what we got available.
Yes, that's
Like,
what
like,
Where is there right Oh, yeah.
seriously?
Yeah. I looked at it.
Sarah is looking to like order it. Okay, if you want to, you can grab a Chromebook from Mrs. Elmarger. If you don't, that's fine too. I know there's not a lot of time, so. I've got them tomorrow, so you guys can have a work day tomorrow on here.